Hello, my name is Andrew Caratu. I'm a teaching assistant at MathTopia Academy, and in this video, I will be doing problems 1 through 5 of the 2022 AIME I. So yeah, let's get started. Okay, so quadratic polynomials P of x and Q of x have leading coefficients of 2 and -2, respectively. The graphs of both polynomials pass through the points 16, 54 and 20, 53, and it's asking us to find P of 0 plus Q of 0. Okay, so, well, we know the leading coefficients of a parabola help determine what the shape of it will be, right? So we know P of x having a leading coefficient of 2 will look something like this. It'll be facing up because this leading coefficient is positive. And we know it'll be passing through this point 16, 54 and this point 20, 53. And then the other parabola Q of x will be the same thing as P of x, but it'll kind of be facing the other way. So it'll look something like this, right? And these are our points, 16, 54, and 20, 53. So, well, we can think about what the relationship between these two parabolas is, right? Like, we know that they're very similar to each other in that they both have, that if we take like the absolute value of their leading coefficients, it's the same. So they both kind of have the same shape to them, right? It's just that one of them's facing up and the other one's facing down. So we can think about maybe a 180-degree rotation, right? Because if we rotate one of them 180 degrees across some certain point, we might end up at the other parabola. So we can think, what kind of point could we rotate about? And well, we have to pick a point that if we rotate about this point, we end up here. And if we rotate this point about it, we end up here. And there's only a single point that meets those requirements. And that's obviously the midpoint of those 2 points, which is 18, 53.5. And the special thing about this point is that if we take this parabola P of x, right, and we rotate it across this point, we'll end up with a parabola. It'll have -2 as its leading coefficient, right? And it'll pass through these 2 points still, right? Which means it has to be Q of x because there's only one parabola that meets those requirements. So basically, rotating P of x 180 degrees across this point must give us Q of x. So I'll move this over. And we can use this to help solve the problem, right? Because let's say P of x, right? P of x, we can give as ax squared plus bx plus c. But actually, we know the leading coefficient is 2, so we can write it as this. 2x squared plus ax plus b, right? And then, well, the thing is, we can replace this P of x with a y, and then in order to get what Q of x would be, we can just rotate it 180 degrees across this point, right? 18, 53.5. And the way we would rotate 180 degrees across a point is we would kind of reflect across the point, which I mean by reflecting across this value and then reflecting across this value. So first we would reflect this parabola across the line x equals 18, and then reflect it across the line y equals 53.5. And if we do those 2 reflections, it'll give us the rotation. So in order to reflect across x equals 18, right, which is like this sort of line at 18, well, every point like over here will have to reflect to a point like over here, right? And the thing about their x values is that, let's say this is 18 minus a, we would know this would have to be 18 plus a, which means the sum of these 2 values would always have to be twice as much as 18, which is 36, right? So what we do is we replace x with 36 minus x, right? Because their distances from 18 will both be 18 minus x. Same thing with y equals 53.5. Well, if we start at y, well, it must be subtracted from twice as much as 53.5, which is 107. So what we can do is we can take this equation and we can replace it with those values. And what we end up with is 107 minus y is equal to 2 times 36 minus x squared plus a times 36 minus x plus b. And what we can do from this is we can determine what q of 0 and p of 0 is, because this is the formula for q of x, right? Except the y isn't really in its like optimal location, which is isolated, but that's okay, because all we have to do is plug in x equals 0 and then solve for y. So if we plug in x equals 0 over here, what we get is y equals b, right? So that's what p of 0 is, it's b. And if we plug in x equals 0 over here, well, we'll get a little bit something more computation heavy, but that's okay. 107 minus y is equal to, well, this is just going to become 2 times 36 squared, right? 2 times 36 squared. So I'll just write that. And then over here, if we plug in x equals 0, we end up with 36a, and then we add on b, right? So basically what we do is we can subtract the 107, and then invert everything. So we multiply everything by -1 in order to get rid of the negative in front of the y. So that becomes negative, that becomes negative, that becomes negative, and the negative 107 becomes positive. So we end up with this as q of 0, right? So if we add the two up, right, p of 0 and q of 0, what we'll just end up with is -2 times 36 squared plus 107 minus 36a. So the only thing we need to find now is the a, which is basically the x term, the x coefficient in p of x. And we can find this simply by plugging in, right? Because we know 2 times 16 squared plus 16a plus b would give us 54. Meanwhile, 2 times 20 squared, if we plug in 20, plus 16 times, plus 20 times a, plus b would give us 53. And then we can just subtract these two equations, right? If we subtract this equation from this equation, what we'll end up with is, well, 20 squared minus 16 squared is just 12 squared, 144, times 2 would just give us 288, right? Plus 4a is equal to -1. So if we subtract 288, we end up with -289, and then what we'll end up with is a is just -289 over 4. So I'll move that over a little bit. And then from here, we can just solve the problem, because we know the answer would just be this. And then minus 36a, well, the minuses from here and here would cancel out, right? So we just end up with 289 over 4 times 36, which the 36 over 4 is just 9. So we're just adding on 289 times 9, right? So we can do a little bit of multiplication. It's not that bad. -2 times 36 squared. Well, that would just give us -2,592. Yeah. And then add on 107. And then what we get for this part, well, you can just say this is 300 minus 11, right? So we just get 2,700 minus 99, which would just be 2601. And if we add all this up, we'll get our final answer of just 116. Yeah. Okay, nice. So let's go on to number 2, which says, find a 3-digit positive integer, a, b, c, whose representation in base 9 is BCA. Well, so the digits kind of cycle a little bit. So as you might know, the way bases work is that the first place is 1, the second place would be the base, right? 9 in this case. The third would be the base squared, so 81, and so on, right? So that's why in base 10, right? This is the hundreds place, this is the tens place, this is the ones place. So we get our coefficients, right? We get 100a plus 10b plus c is equal to 81b plus 9c plus a, right? So if we simplify things a little bit in this equality, we get 99a is equal to 71b plus 8c. So all we need to do is find three numbers, A, B, and C, that satisfy this equality, right? So the thing is, we have to find these two numbers being like close to each other. We need to find them being close enough to each other that C can exist, right? However, in most cases, right? Like for example, if we say A equals 1 and B equals 1, right? Then we get 28 is equal to 8C, right? And 28 is small enough to give C a value, but it's not a whole value. C is going to be, in this case, 7/2, right? It's 3.5. We can't have a digit be 3.5. So we need this 99A minus 71B. We need it to be between 8 and 72. It can actually be between 0 and 72. It has to be between these two numbers, and it has to be a multiple of 8, right? So what we can do is we can try writing down the multiples of 99, right? 99, 198, 297. There's a very easy pattern you can see. So you can very easily write down all the multiples here. Yep, and we just include, yeah, A from 1 to 9. A can't be 0 because the leading digit can't be 0. And also notice that B can't be 0 because this leading digit has to not be 0. So we write down, right, 71, 142, and this one, yeah, we can also pretty easily find all the values, right? Because this part's just the multiples of 7, right? 7 times 4, 7 times 5, 7 times 6, 7 times 7, 7 times 8, 7 times 9. And then these are just the digits going up. So 4, 5, 6, 7, 8, 9. So we write down all of these, right? And now we have to find certain differences that work, right? Between 0 and 72. So for example, 99 and 71, right? This difference would work, but it's not a multiple of 8, right? So it can help to write down the mod, like we can take these all in mod 8 and see what we get, right? Because we can only pair together numbers that are the same in mod 8, right? So if we write down these in mod 8, well, 99 is 3 in mod 8. So it goes 3, 6, 1. We just keep on adding 3. Right, like that. And then in this case, it would be, this is 7 actually. So 7, and then 6, 5, 4, 3, 2, 1. So these are all the modulars. This is everything in mod 8, right? So now we can pretty easily see what we can pair together in mod 8, right? So these two numbers, right? 99 and 891, we can only pair with 355. But the differences between them are so large that none of them would work. So these three are out, right? And then if we move on, right, this 7, right, these two 7s in mod 8 can only pair together with this 7 in mod 8, but the differences are once again way too large, so they're all out. With these two, right, the two zeros, they're actually pretty close to each other. They're only 200 apart, but remember, we have to have them be 72 apart. So this is still too big. So those are out. We can take the ones in mod 8, right? 297, 497. But once again, the difference is too large, so they're out. These two numbers, right? Their difference is actually very close. It's less than 200, but it's still more than 72. So they're both out. These two numbers, right? They're both out. Their difference is like 400 something. These two are this, like, they take like a, like they're almost close enough. The difference is only 112, but they're out. And like the only ones that we have left are these two. And if we look at these two, sure enough, their difference is only 56. So I just went through all the other ones first so we could see that there is no other solution other than this one. So 198, which is A equals 2, and 142, which is B equals 2, right? And then 56, well, C would be that over 8, so C would just be 7, and we can get our answer as just 227. Yeah. Yep, and that's pretty much it. I mean, another way you could have done this, like, because this problem is actually kind of set up where you could probably skip a lot of the casework if you have a bit of a clever eye, right? Which I actually kind of did when I was solving this. Like, what you could see immediately is like when I originally said, oh, let's just plug in A equals 1 and B equals 1 just to see what we get, right? And you see, right, we get 28 and 8C, right? And the thing is, this doesn't work because C is 7 over 2. But what you can immediately see is we can just scale up all three numbers, A, B, and C by 2, right? Like this is 1, 1, 7 halves. If we scale them all up by 2, we'll just instantly get a solution, right? So that's kind of another way to think about it. So if you saw that, you could potentially skip a lot of casework. Anyways, so let's move on to number 3. So this one is talking about an isosceles trapezoid, right? So I'll just draw it right here. So it says we have an isosceles trapezoid ABCD. We have parallel bases AB and CD, and they have, and it just gives us the lengths for the isosceles trapezoid, which is nice. Just gives us all 4 lengths. And here's what it's asking. It's actually asking something very simple. Take this angle bisector, take this angle bisector, see where they intersect, take this angle bisector, take this angle bisector, see where they intersect. So angle bisector, angle bisector, angle bisector, angle bisector, and we just take their intersections. And all it's asking for is this length. This is the whole problem right here. It's just asking for that length. But what you might quickly see is that it's much harder to find a good way to come up with this length than it looks, because I mean, we only have angle bisectors here. And what you might quickly see, right, is that the sum of these two angles, right, if we take the sum of those two angles, what we'll end up with is 180. So the sum of half of that angle plus half of this angle is 90. So therefore, this is a right triangle. This is a right triangle, right? But we still don't know like where this point is, right? All we know is that it has to be on this semicircle. It could be anywhere on the semicircle. But what kind of trivializes the problem is if you think about dropping altitudes from this point. Like let's say I drop an altitude, and then I drop another altitude, and then I drop another altitude. Well, what happens is, let's say we call this X, right? Well, what would this length be? Well, we know that this is an altitude and this is an altitude. So this is just a full altitude, right? So if we drop this altitude, this is X, and this, well, we know that this length here, if we drop this altitude as well, this length is 500, right? So this length plus this length has to be 150. But we know they're both equal because it's an isosceles trapezoid. So we know these are both equal to 75. So essentially, this would have to be equal to 75. So ignoring this altitude, this length here is just X plus 75. But the thing is, what is really nice about the angle bisectors, these equal angles, is that we can instantly see that these two triangles are congruent and these two triangles are also congruent, right? Because we have equal angles, we have an equal second angles, and we have this equal side between them, right? Like AAS congruency, we instantly see these two triangles are congruent, right? Same thing here, AAS, right? AAS, AAS, right? So we instantly see these two triangles are congruent, these two triangles are congruent. So we can just move this length over here, x plus 75, x plus 75. And we instantly see this makes the problem trivial because all we're looking for is PQ. And if we drop this altitude here as well, right? This is x, right? If we're just looking for this length here, PQ, this goes over to here, right? 500 minus 2x. So all we're looking for is 500 minus 2x, but we know 2x plus 75 is equal to 333 from right here. And all we're looking for is 500 minus 2x. So, well, what we can do, right, is 500 minus, and then we know 2x is 333 minus 75, right? So what we get is just plus 75 minus 333. And this is going to be our answer right here. And if we just subtract, we end up with 242. Yeah. 242. Yeah. So yeah, if we solve for x directly here, we would get x is 129. So yeah, that checks out. Very nice problem. All right, moving on, number 4. So this one is talking about complex numbers, right? So this one is kind of like, there's always in an AIME test, there's always like at least one problem where it requires you to have some prior knowledge about complex numbers, right? It tells you W is the square root of 3 plus I over 2, right? And Z is -1 plus I times the square root of 3 over 2. And it's asking us to find the number of ordered pairs RS of positive integers that don't exceed 100. So what it's really saying is R and S are from 1 to 100. And it has to satisfy the equation I times W to the power of R is equal to Z to the power of S, right? So let's draw our complex plane. And what we can see from here is W is root 3 plus I over 2. So it would be right about here, right? This is where W would be. And Z is -1 plus I root 3 over 2. So be probably like here. So the thing is, right? We know a 30, 60, 90 triangle, right? Given that its hypotenuse is length 1, we know that this length here is 1/2, and this length here is the square root of 3 over 2, right? So essentially, we know that since this is the square root of 3 over 2, and this is 1/2, we know that this W is actually, it's the number that represents a 30-degree rotation, right? And Z, we know, well, this is going to be 60. So subtracting from 180, we know Z is the number that represents a 120-degree rotation, right? It's 120 degrees rotated from 1, right? Because both of these have hypotenuse 1. And basically, the way we can think about this, I times W to the power of R is equal to Z to the power of S. Well, we know from complex numbers, the way complex numbers work is that when you multiply them by themselves, right? Like if we multiply W by itself, right? When we multiply two complex numbers, right? Let's say A and B, what you do is you take the angles, right? The angles between them and the positive x-axis, and you add those two angles, right? And then you take their radii and you multiply them, right? So you multiply their radii, right? And you add their angles. So in the case of numbers like W and Z and I, right? All three of those numbers have in common that their distance from the origin, right? Their radius is 1, right? So we don't have to worry about this. We don't have to worry about this because 1 times 1 is 1, right? Just going to stay as 1. So we can just ignore this. And since we know all the radii we're dealing with in this problem are 1, all we have to think about is their angle measurement, right? So, well, the thing is, I represents a degree of 90, right? Like we said, W represents a degree of 30, and Z represents a degree of 120, right? So what we can think about is if we multiply W by itself R times, right? We're taking the 1 radius and we're multiplying it by itself R times, but that's just going to give us 1, like we already said. But the angles are what's really cool, because what we actually get from this is that the angle measurement of W to the R is just 30 times R, because we're adding 30 to itself R times. And that's the definition of multiplication, right? We're just adding the number to itself that number of times. That's what multiplication is. So it's just 30R, right? And then multiplying by I is actually just saying adding 90 to it, right? Because what we just said, we add the angles. And then what we'll get on this side is just 120 times S. And that explains to us what happens in this diagram, right? Because we know W as measure 30 and Z has measure 120. And if we multiply it by I, we're just going to end up at Z, right? Because we're rotating counterclockwise by 90 degrees when we multiply by I. And that's why R equals 1, S equals 1 is one of the solutions, right? So now all we have to do is just solve this equation, which we can simplify even further by just dividing by 3. But dividing by 30, I mean, dividing by 30. So we can just solve the problem from here. So if we think about it, right, for every value of S, right, R has its own value of 4S minus 3, right, for every value of S we pick, right? So S could be a number from 1 all the way up to, oh yes, my bad. There's actually one more thing that we haven't addressed, and that's the fact that if we rotate 360 degrees, we actually end up back where we started. So actually, these are only equivalent to each other in modular 360, right? Like for example, if we take R and we set it to 13, right? If we set R to 13 and then we set S to 1, right? It's still going to work because this is going to give us 390 plus 90, right? But the thing is, it's in mod 360 actually. So we subtract the 360 from here and we end up with 30. So it's equivalent to 120, right? So actually we have to take it in modular 360. So when we divide by 30, right? We also have to divide the modular by 30. So this is actually just in mod 12. So yeah, that's something I completely forgot about. So we have to deal with this on a case-by-case basis, right? So S could either be 1 in mod 3, 2 in mod 3, or 3 in mod 3, right? This is what S could be in mod 3. And depending on what it is, we either get that this is 4 in mod 12, 8 in mod 12, or 12 in mod 12, right? So the thing is, for S to be 1 in mod 3, well, there's a total of 34 numbers that work like that. 1, 4, 7, 10, all the way up to 100. For S being 2 in mod 3, there's 33 numbers, right? 2, 5, 8, all the way up to 98. And then for 3 in mod 3, there's also 33, right? 3 all the way up to 99. So if we do it like this, well, in the case where S is 1 in mod 3, we get that 3 plus R has to be 4 in mod 12, which means R has to be 1 in mod 12, right? So that means R would have to be 1, 13, right? We can add 12 again, we can add 12 again, up until 97, right? Which would be 12 times 8 plus 1. So this is 12 times 0 plus 1, and we're going up to 12 times 8 plus 1, right? So that from 0 to 8, that's 9 numbers. So 9 over here. Well, what happens if we say S is 2 in mod 3? Well, 4 times 2 gives us 8. 8 minus 3 is 5. So R would have to be 5 in mod 12 this time. So we would go 5, 17, keep on adding 12, keep on adding 12 until we end up at 89, right? 89, which is 12 times 7 plus 5. We go from 12 times 0 plus 5 to 12 times 7 plus 5. That's a total from 0 to 7. That's 8 numbers. And then finally, right, if we plug in S is 3 in mod 3, well, we get that this is just 12 in mod 12. Subtract 3, we get 9. So R would have to be 9 in mod 12. So how would we do this? Well, we take 9, then we add on 12, right? We add on 12, we keep on going until we reach 93, right? Which is 12 times 7 plus 9. Yeah, 12 times 7 plus 9. So this is 12 times 0 plus 9. This is 12 times 7 plus 9. So finally, we get 8 numbers over here as well. So we get this, right? These 3. So what we get is just 34. 34 times 9 plus 33 times 8 plus 33 times 8, right? And what we can actually do is we can just take out a 34 from here to make the math easier. This right here, this is just 100 times 8, which is 800. So our final answer is just 834. Okay. Finally, we're at number 5. All right. So this one is actually a very cool problem. So we have a straight river, right? So let's draw in our river. It's 264 meters wide, and it flows from west to east at a rate of 14 meters a minute. So every minute it goes 14 minutes to the right, right? So Melaine and Sherry start, right? They start at their own points. Let's just draw them in, right? Let's say they start here and S starts here. And Melanie is D, right? Is D away from Sherry, right? And then, okay, actually, Melanie is downstream from Sherry, right? Sherry's more upstream and the water's flowing this way. So Melanie is a distance D downstream. So it's actually Melanie's over there. And Melanie swims this much, right? And Sherry swims this much, right? Because they have to get to the same point, right? That are the same distance away from each of them, right? And they each arrive at the same point at the same time. So everything is basically equal, right? Everything is equal, everything is even, except for the fact that Sherry only swims 60 meters a minute and Melanie swims at 80 meters a minute, right? And you might be wondering, how do they go the same distance and arrive at the same time? Well, that's because of this current that's pushing them, right? Because Melanie is actually swimming in this direction, and Sherry's actually swimming in this direction, right? Because Sherry's swimming in this direction while the current's pushing her is going this direction, right? And Melanie, while she's swimming in this direction, the current's pushing her this direction, right? So in actuality, if we finish these two vectors that actually mean something in the problem, right? Then it's actually like this. This is actually how it looks. So this is basically, this is, right, the current pushing them. But if the current wasn't there, they would actually go this, right? So ignoring the current, it's like this instead. And this is much more helpful to work with because we know that the ratio of this to this is actually 3 to 4, right? Because we have no current to worry about. Since they both complete this in the same amount of time, right? That means that the ratio between them must be the ratio of their speeds, right? So Sherry swims 3/4 as much as Melanie because Sherry's only going 3/4 the speed of Melanie. So they both swim in straight lines towards this point. And at this part, it's very helpful to drop an altitude because we know that this is 264. And we also know that the difference of these two values, right? The difference of this minus this, those two distances, the difference between them, we know it has to be related to x, right? So let's try to find that out, right? Let's call this, I'll call this point P, right? Let's ignore distance D. We don't need to write D. So we can say that SP is Y, right? Well, then what would PM be? Well, let's see, how long does it take for Sherry and Mulaney to reach this point, right? Well, let's think about it. If Sherry's going 3x meters and is swimming at 60 meters a minute, well, then that means that the amount of time in minutes it must take is 3x over 60, right? Which is equal to x over 20. So it takes each of them x over 20 minutes, right, to get where they end up, right? So from here to here, right, and here to here, the time elapsed is x over 20. Well, in those x over 20 minutes, the river is going to flow 14 times that, right? Because it's 14 times the number of minutes. That's how much, right? Because it's going 14 meters every minute. So it flows this much, which is 7x over 10. So essentially what happens is the river is going to shift them over by 7x over 10. So this distance here, right, to this point, which is the midpoint, right? It has to be the midpoint because that's where it's equidistant for both of them, right? 7x over 10, this distance. Therefore, right, if this right here is y, then this right here has to be y plus 2 times this much. So 7x over 5, right? And that's because when this shifts over by 7x over 10, this length, we will add 7x over 10 to it. And this length, we will subtract 7x over 10 from it, right? And we'll just end up with both of them being y plus 7x over 10. Okay, so now we have completely ignored the current. We are completely done with the current because now we know the distances of everything without the current. And now we have both of these two right triangles. We have two variables, x and y, and we have two right triangles. So we can solve for x and y, right? But we have to be careful about how we do it because if we do it the way you might just approach it, right? You just make this equation, and then you solve for each of them. You'll probably end up with a mess, right? So we have to approach this in a better way than that. And the best way to approach things is to realize that this number is what's really going to make things messy, this 264, because 264, when we square it, we're just going to end up with a mess, right? So what we should do instead is we should focus on what this number represents. Well, this number, right, 264 squared is equal to this number squared minus this number squared, but it's also equal to this number squared minus this number squared. So now we can just set up the equations like that, like this. So 9x squared minus y squared is equal to 16x squared minus y plus 7x over 5 squared, right? And if we simplify things a little bit, right, if we expand this square and we subtract 9x squared from here to get 7x squared over there, right? And in general, we just simplify things a little bit, moving things around, we'll very quickly end up with 49x squared plus 70xy is equal to 175x squared. And now from here, we can simplify things even further by subtracting again, right, the x squareds, and then dividing by x. And what we'll get at that point is just 70y is equal to 126x, right? So simplifying, we divide by 14. 5y is equal to 9x. Well, this is essential. We don't need to, we can get rid of all this because this is what we really care about, the relationship between y and x. Because from here, we can very easily solve for both of them. We can use this part, right? Because it's much more clean. If we use it, right, 9x squared minus y squared is equal to 264 squared, right? So what we can do at this point is just plug in. Well, we can say y. Well, y is just, if we divide by 5, is just 9/5 x, right? So if we square things here, we get 9x squared minus 81 over 25 times x squared, right? And this would be equal to 264 squared. So now what we can do is we can multiply by 25. And at this point, it might look like things are going to get really messy because now we're taking this 264 squared and we're multiplying it by 25. Like that's a huge number. But realize that when we subtract these two, what we'll end up with is just 144x squared. So we can just take the square root of both sides. 12x is 264 times 5. And now if we divide by 12, we'll see 264, that's a multiple of 12. That is just 22 times 12. So x is just 22 times 5, right? And that's just 110. And y is just 9/5 of that. 9 over 5 times this. The 5s cancel. We're just left with 22 times 9, which is 198. So our final answer is just, well, what we're looking for over here, we're just looking for 2y plus 7x over 5. And that answer is just going to be 396, right? Because 2 times y plus 7x over 5, which is just 154. If we add those two together, we're going to end up with our final answer of 550. Yeah. All right. Yeah. So there's actually another way you can solve number 3. So from what we did before, right, drawing in these altitudes, what you can also do, right, from here, instead of finding this x plus 75, right, we sum these two. What we can do instead is focus on this length and then move it over to this length, right, by congruency again, over to this length. These two are equal, right? Similarly, we find these two are equal, and we realize that actually this line, PQ, is actually just on the midline of the trapezoid, right? So if we extend them to these two sides, well, now we have the midline. And actually, we have this whole length here, right? We know this whole length. That's just 500 plus 650 over 2, right? And then what we can get the same here, right? Here, this length. Well, from this right triangle, right? We know that in a right triangle, right? This is the median of the triangle. So it divides it into these 3 equal lengths, right? This length is equal to this length is equal to this length. So this is just 333 over 2. So we want to subtract 333 over 2. And same thing over here. That length is also 333 over 2. So now what we get is just this length plus this length minus this length over 2, right? And we're going to get the exact same answer again, 242, right? And actually what's really cool about this approach to solving the problem is that it doesn't matter if the trapezoid is isosceles. Like this length here, right? Like this length here could be like, I don't know, it could be, what could it be? It could be 400 instead, right? It could be 400, and this length could be like 300. Everything we just mentioned in the problem, it still applies, right? This is still going to be the midline, and then this is going to be 400 over 2. This is going to be 300 over 2. So in general, if we have just a normal trapezoid, doesn't matter if it's isosceles, if this is like A, B, C, and D, we know our answer would just be A plus C minus B minus D over 2. So yeah, that's kind of a generalization for the problem. Very nice. So yeah, this was the numbers 1 through 5 of the 2022 AIME I.